Hi everybody, this is lesson 79, writing an explicit rule for an arithmetic sequence. During this video, if you want to pause it and take some notes, or pause it and work out some problems and then replay it or continue on with the video, that's probably a good idea, so then you can kind of check yourself and see if you're able to do it on your own. All right, one of the words that you need to know when we go through this lesson is explicit equation. So it's an equation, it's a rule, it's a formula, all of those things kind of go together, but it is something that models a particular sequence. You input the position value in for the variable, and the equation will output what term is in that position in the sequence. So today we're going to recognize that arithmetic sequences can be expressed as linear functions, and we're going to write explicit formulas or rules for arithmetic sequences. So here we have a sequence 0, 3, 6, 9, 12. And so with this sequence, we can see that we are adding 3 each time. So we're going to write that in our rule box, that we are adding 3 each time, and that makes this arithmetic. So when we talk about position number, we are talking about there are numbers that are first, and then there are numbers that are second and third and fourth and fifth and so on. So when we talk about term number, we're talking about what position this value is in. So we have the first, second, third, fourth, and fifth numbers, and so I have that filled in for term number, or position number would also work. And then the value, what numbers are actually there, are 0, 3, 6, 9, 12. So this is saying that 0 is first, 3 is second, 6 is third, 9 is fourth, 12 is fifth. And what we're going to do is we're going to graph these. So I am going to have 0, 1, 0, 2, 3, 3, 6, 4, 9, and 5, 12 doesn't fit, but I've got a good, at least a good 4 of them on here. Now, we are not going to connect these. This is discrete, so we do not connect the dots because we're not using all the numbers between 0 and 3 and the numbers between 3 and 6. We're just using those individual values, okay? But if you notice, this is arithmetic and we're adding 3 each time. If I was to connect these with a straight line, that would be linear, and the slope would be up 3, right 1, up 3, right 1, up 3, right 1. So it would have a slope of positive 3. So this is an arithmetic function, and all arithmetic functions can be represented by linear functions. And so that's going to get into what kind of equation we're going to write later. Let's look at example 2. We've got 4, 2, 0, negative 2, negative 4. So the rule is, the pattern that we can see as we go to, to the next number is that we are subtracting 2. Again, adding and subtracting the same number each time, that means it's arithmetic. All right, so we have the first number, the second number, the third number, the fourth number, the fifth number, and which number's first? 4. And then 2 is second, 0 is third, negative 2 is fourth, and negative 4 is fifth. And if we graph those, we again will be able to see that this is very linear and that we are subtracting 2 each time. That creates a slope of down to right 1, down to right 1. So it's still discrete. It's modeled by a linear function. And because we're subtracting 2 each time, its slope is negative 2. Isn't that cool? All right, example 3. We've got 8, 5, 2, negative 1, and negative 4. Oh, I've got an 8 there already. All right, let's see if we can figure out the rule. Well, our numbers are getting smaller, so that means we're going to be subtracting. And it looks like we're subtracting 3 each time. So again, subtracting 3 is going to be arithmetic. So when we go to graph these, we should expect to see a line start to form. Again, don't connect the points, but the slope of that line should be negative 3. So let's see if that's true. So here's our first, second, third, fourth, fifth, and then we've got 8, 5, 2, -1, -4. If we graph those, and if I look here, down 3, right 1, down 3, right 1, down 3, right 1, down 3, right 1. So it has a slope of -3. That's pretty neat. All right, so it's still discrete, modeled by a linear function, subtracting 3 each time, slope of -3. All right, example 4. If you think you can figure this out and graph it, go ahead, pause it, and do it yourself, and then we'll start it back up and see how you do. All right, -5, -1, 3, 7, and 11 is our sequence, and it looks like our rule is adding 4 each time, so we should expect to see a slope of 4. There's our term values, our position, and here is our values, what number's actually in that spot. And if we graph it, there it is. You can squeeze 11 up here. It's up at the tippy top, but it'll fit. And if I look at this, up 4, right 1, up 4, right 1, up 4, right 1, up 4, right 1, we're looking good. Slope of 4. Again, still discrete, modeled by a linear function because it's arithmetic, adding 4 each time, so we have a slope of +4. Looking good. All right, so arithmetic sequences have a constant difference. A constant difference, and sometimes that's called a common difference. Common difference is represented by the little lowercase letter d, okay? And that's what you're adding or subtracting to get to the next number. So if you're adding to get to the next number, this will be a positive value. If you're subtracting, it'll be a negative value. And the common difference has to be the same all the way throughout. Now, if you're having trouble figuring out what the common difference is, you can always take the second number and subtract the first number. So 3 minus -1 would be 4. Sometimes it's a little bit difficult at the beginning. If you want to skip down to a little bit further, you can take the number on the right and subtract the number on the left. So 11 minus 7 is also 4. So it's a little way to figure it out, and that's why it's called common difference, because they're all common, right? They're all happening, has to happen all the way throughout, but the difference part comes from the second number subtracting the number in front of it. All right, arithmetic sequences are modeled by linear functions, and that's always. And then the next part, this explicit rule, I have a formula for you. Now, this formula I expect you to have handy when you take a quiz or a test, because this is like how you're going to write your explicit rules. So definitely make sure you write explicit rule, arithmetic sequence, and here it is. Now, some of these pieces look a little bit weird. So we have this piece and this piece. Definitely, we're going to have to talk about them. This is your common difference, and this is the position. And I'm going to have some different things pop up, but these guys are new. And the reason why people struggle with explicit rules, and then later on we'll talk about recursive rules, is the notation. So this is A, and then the little n, you read it sub n. So this is A sub n, and it takes the same place as y, like y equals. And what this is this is the nth term. Nth is a really good, if you play Scrabble, nth is a really good word if you don't have any vowels. It's in the dictionary, I promise. It's the nth term. And that n takes the place of the position. So if I want the 22nd term, this would be A, and I would write a little 22. If I want the 105th term, this would be A, and I put a little 105 down here. So that represents a specific term. When you don't know what term it's going to be, it's just going to be with an n down here. So that's A sub n equals A sub 1. Now, A sub 1, there's a number there. There's not an n. So that would mean that this is the first term. So whatever the first number is, that's going to go in that spot. All right, we're going to skip to n. N is the position number. It's usually when we are dealing with writing the rule, writing the equation, this is going to be a variable, as well as A sub n is going to be a variable. So it's almost like it takes the place of x, and A sub n takes the place of y. But most of the time, you're going to see it just be a variable. And then The lowercase letter d right there is going to be your common difference. So really, to write these, you just need to know the first term and the common difference to write the explicit rule for an arithmetic sequence. So here I have the formula up on top. And what we're going to do is we're going to write the explicit rule. Now, for the first two, 5 and 6, we actually have to figure out what the first term is and what the common difference is. For 7, 8, and 9, they already give it to us kind of spelled out. So what we're going to do is for 5 and 6, we're going to figure out the first number in the sequence, which that's going to be a sub 1. And then we're going to figure out the common difference, what we're adding or subtracting each time. That's going to be the little lowercase letter d. And pretty much we're just going to pop them into the right spots, and then we'll be done. So for number 5, our first number is 11 because 11 is written first. So for number 6, the very first number is 85. So a sub 1 is 85. All right, let's go back to number 5. What are we doing each time to get to the next number? Looks like we're going up, so that would mean that we're adding. We are adding 9, because if I take 20 and subtract away 11, 20 minus 11 is 9, or 29 minus 20 is 9. All right, for number 6, let's see our common difference. We're going down, so that means it's going to be a negative number. Looks like we're subtracting 8, so the common difference would be negative 8. All right, so the rest of this, once you have those values, now I have everything that 7, 8, and 9 have, right? I have a sub 1, I have d. So what I want to do is oh, look at there. There's all my formulas. Okay, and what we're going to do is we're just going to pop these numbers in the right spots. So for a sub 1, we're going to put in an 11, and for d, we're going to put in a 9. And there we have our explicit rule. And we're done with number 5. Number 6, we're going to plug in 85 in for a sub 1. Now, we're going to plug in negative 8 for our common difference. And you can put plus negative 8, or you can write minus 8. I put minus 8. But that's it. That's our explicit rule. All right, so number 7, we're going to plug in a 15 for a sub 1 and a 5 for the common difference. And we're done. For number 8, we're going to plug in a 3 for the a sub 1 and a negative 11 for the common difference. And then for number 9, we're going to plug in a 0 for a sub 1 and a 3.5 for our common difference. Now, because there's a 0 already there, we could just write this as a sub n equals 3.5 times n minus 1. All right, so you can simplify these rules, and sometimes you will need to. So there are 2 steps. First, you're going to distribute the common difference, and then you're going to combine like terms. So for number 10, I'm going to distribute this 6 into the parentheses, and then I'm going to combine like terms. Do not add the 31 and the 6. That's not going to work. Distribute first, and then combine like terms. So for number 10, I'm going to distribute the 6, and then I can combine 31 minus 6, so I end up with 6n plus 25. And that is the simplified arithmetic rule. All right, number 11, let's distribute that 1/2. So I've got negative 2 plus 1/2 n minus 1/2, and then I can combine negative 2 and negative 1/2 and get 1/2 n minus 2.5. or 2.5 or 5 over 2. I'm not going to be really picky about those because you should know by now that all of those are the same thing. All right, number 12, we're going to distribute the negative 2 first, and then we're going to combine the negative 19 and the positive 2. Negative 19 plus 2 is negative 17, so we've got negative 2n minus 17. And then number 13, we're going to distribute the 1, which technically we don't need to. And then we'll combine negative 1 and negative 1/4 and get n minus 1.25 or 1 1/4 or 5/4. All right, now let's look at how to use this sequence. What we have for these problems is we have an explicit rule already written for us, and they want us to find specific values. So the 13th term, the 20th term, down here, we have it written with the other notation. This is the 42nd term and the 100th term. And the key to this is If they give you a specific number, you're just going to plug that number in for n, and you're going to simplify. So for number 14, we want the 13th term, so we're going to plug in 13. Now, I'm going to put 13 down here for n so that I have a symbol to tell me that, hey, I'm looking for the 13th term. We plugged in 13 for n, do a little bit of subtraction. 13 minus 1 is 12. And then at this point, you multiply the 12 times the 6 and then add the -7. You could stick it in a calculator as well, but the 13th term is 65. So anytime they want you to use the explicit rule to find a specific term, you are just plugging that value in for n, and of course you're following the order of operations. So number 15, the 20th term, we're going to plug in 20. 20 minus 1 is 19. 19 times 6 plus a -7 is 107. So the 20th term is 107. For 16, we're plugging in 42 for n. So we'd do 42 minus 1 is 41. 41 times 6 plus a -7 is 239. And I just typed these into my own calculator. So you are more than welcome to plug them into the calculator and get an answer. Just if you don't have like one of the graphing calculators where you can type everything in all at once, you'll need to make sure you follow the order of operations. All right, last one, we're going to plug in 100. 100 minus 1 is 99. 99 times 6 plus a -7 is 587. So the 100th term is 587. All right, let's look at pulling it all together. So we're going to be given a sequence. We're going to write the rule. I'm also going to have the simplified rule there for you when we go through these answers. And then I'm going to show you A sub 15, A sub 50, and A sub 100. So this is a really good one to pause the video on and try to do some by yourself, and then go back through and hear a little bit of the reason why things are going that way. So if you want to pause the video now and see if you can fill out this table, that'd be awesome. All right, number 18, what we're going to do first is we're going to identify the A sub 1 and the common difference. So our A sub 1 is going to be 1,000, and our common difference, we're subtracting 250 each time. So I'm going to plug them in for A sub 1 and for the common difference to create the rule. So A sub n equals 1,000 minus 250, parentheses n minus 1. And then if I distribute that -250, I would end up with -250n plus 1250. I'm going to plug in 15. It doesn't matter which one that you use, if you use the explicit rule or the simplified explicit rule, but we're going to plug 15 in for n and get -2,500. If you plug in 50 for n, you get -11,250. And if you plug in 100 for n, you get -23,750. All right, number 19. Our A sub 1 is 13. Our common difference is 11 because we're adding 11 each time, or you could do 24 minus 13. That's 11. I'm going to plug in A sub 1 and the common difference into my equation. So I'm going to get A sub n equals 13 plus 11, parentheses n minus 1. Or if I distribute that 11 and combine like terms, I'll end up with A sub n equals 11n plus 2. All right, we're going to plug in 15. Doesn't matter if you plug it in for n here or n here, but what we're going to do is plug in 15 and work that out, and you should get 167. If I plug in 50 in for n, I should get 552. And if I plug in 100 for n, I should get 1,102. All right, number 20. -2, -5, -8, -11. So my first number is -2. My common difference, I'm subtracting 3 each time. So common difference is -3. My formulas are A sub n equals -2 minus 3, parentheses n minus 1. Or if I distribute that -3 and combine like terms, I end up with A sub n equals -3n plus 1. Plugging in 15, I get -44. Plugging in 50, I get -149, and plugging in 100 for n, I get -299. All right, last one. I've got 0.1, 0.3, 0.5, 0.7. My A sub 1, my first term is 0.1. I'm adding 0.2 each time. So my rule is going to be a sub n equals 0.1 plus 0.2 times n minus 1. Or if I distribute that 0.2 into the parentheses, I get 0.2n minus 0.1. If I plug in 15 for n, I get 2.9. If I plug in 50 for n, I get 9.9. And if I plug in 100 for n, I get 19.9. So there's a lot of stuff going on here, but the main thing is, can we write an explicit rule, and then can we use that rule to predict on way down the road what those numbers are in the sequence? And that's the strength of an explicit rule, is that, if I wanted the 1,000,000th term, all I had to do is plug in 1,000,000 and work that little math problem out and simplify it down to a number. All right, so that's the end of this video. I will see you in the next video.